What if I choose to challenge you with a number operation in algebra? 7x plus 2. What will you say the answer is? Is it 9x? No. 7x plus 2 is not equal to 9x. One could just think that all that is required is to add 2 to 7 and the result becomes 9. In this case, it is not applicable. What makes it wrong to conclude that 7x plus 2 is equal to 9x? What knowledge does someone lack that leads him to making the conclusion that 7x plus 2 is equal to 9x? That takes us to the 7th lesson objective of this lesson, and that is arithmetic of unlike terms. That one does not understand the concept and the properties of unlike terms. He does not know that unlike terms are selective and sometimes stubborn when they take part in basic and other number operations. Sometimes when they take part in number operations, they produce one final and simplified answer. And sometimes when they take part in other number operations, they fail to do just that. When do number operations get us last simplified answer using unlike terms? And when do unlike terms produce no single and simplified answer? Please cooperate with me as I develop this section. In it, I explain and identify the type of number operations where unlike terms do not produce one single, final, and simplified answer. Please cooperate with me as I go through it. Our last objective is number 7, and that is arithmetic of unlike terms. 6 bracket 3 to the power 2 and 2 bracket 3 are unlike terms, and correspondingly 6y to the power 2 and 2y are unlike terms. Why? Look at this and compare it with this. 6 is quantifying how many 3's. In fact, if you should resolve this bracket, you will know that what is inside here is 9. I hope you know why. 3 to the power 2 is 9. So 6 bracket 3 to the power 2 is the same thing as saying 6 9's. Then 2 bracket 3 means 2 3's. So invariably, we know that 6 is quantifying the number of 9's, while 2 is quantifying the number of 3's. Like terms are mathematical expressions in which the same thing to the same power is being quantified. See 6 quantifying 9 and 2 quantifying 3. Consequently, both of them are unlike terms. Somebody might wonder, is 3 not here and also 3 here? Sure, they are there. But notice that this 3 is not on its own. 3 has an operator, that is something going on that makes this 3 soon turn to something different. This 3 is not raised to the power 1. If it is to the power 1, we can regard it as 3. But this 3 is not just 3. When evaluated according to the operation, it is 9. Therefore, a different way of writing 9 is 3 to the power 2. So take it that what is here is not 3, it is 9, except that this 3 and this 3 are the same. But this carries power 2 and this carries power 1. Consequently, the 2 are not the same number. Therefore, 2 different numbers are being quantified. That is why the 2 are unlike terms. 6y to the power 2 is adapted from here. 6 is still there, but this 3 is now replaced with y. The power 2 is still there, is a constant. 2 is still here, and this 3 replaced with y. To learn whether it is possible to get simple end results when we add, subtract, multiply, and divide unlike terms, let us carry out numerical experiments on these two selected base of numbers. In the case of like terms, we discovered through experiments that when we multiply, we get a simpler answer. When we divide, we get a simpler answer. When we add, we get a simpler answer. And when we subtract, we get a simpler answer. And that is why we concluded that addition, subtraction, multiplication, and division of like terms all simplify out. Is that statement applicable to unlike terms? In part, that is what we want to achieve. We want to know whether all the four mathematical operations will simplify out in the case of unlike terms. I want to start with the first numerical experiment that borders on addition of unlike terms. Please watch out. And here comes the first numerical experiment, and that is on addition of unlike terms. Let this be added to this. See it here, 6 bracket 3 to the power 2 plus 2 bracket 3. By default, it is equal to 6 bracket 9 plus 2 bracket 3. I hope you know why this 6 bracket 3 to the power 2 became 6 bracket 9. Obviously, 3 to the power 2 is the same thing as 9. That is why this has become this. And then this remains the same way, that is 2 bracket 3. Now we make progress. 6 bracket 9 means 6 nines. 6 nines means 6 times 9, and that is equal to 54. 2 bracket 3 means 2 threes, and 2 threes will give us 6. Therefore, this number operation will give us 54 plus 6 as one of its results. Then the last result is 60. Therefore, the answer to this number operation is 60 ultimately. Now, if we find a different way of getting the same 60, or at least any of these intermediate results without using this default method, and it appears to be consistent each time when tested, that will be taken as kind of law or a theory of adding unlike terms. But if you try several times, you will not find easily alternative method of simplifying this number operation apart from this default method. So I conclude for now that only default method serves here. There is no alternative method of doing it. In the case of like terms, we used both default method and alternative method. And that method that came to alternative became a law or a principle or a theory regarding the addition of like terms. In the case of these unlike terms, there is no such alternative process. Or do you think there is such alternative process? I mean, do you think we can apply a different method to getting the answer to this number operation? If there is any, please, we can come up with it. For now, there is no such alternative method. Then correspondingly, I'm going to write this 6y to the power 2 plus 2y, and let us see whether the 2 can simplify out. Now see the corresponding number operation, 6y to the power 2 plus 2y. Do you think that these two, when added, will give us anything simpler? The best you can do to simplify this is to factorize this, in which y is a common factor. Even when factorized, y will appear 2 times, one outside the bracket and the other inside the bracket. That might be called a simpler form of this expression, but that is not exactly what we mean when we say simplify out. That is to say, 6y to the power 2 plus 2y will not give us just a single number as in the case of like terms. Because of that, we conclude that it is not possible to add 2 terms which are unlike terms. That is why I wish to conclude that the addition of 2 unlike terms or more is irreducible. That is, 6y to the power 2 plus 2y is equal to irreducible. And that is it. Now we ask also, what about subtraction? What if I replace this sign with sign of subtraction, that is minus, so that what we now have is 6 to the power 6 bracket 3 to the power 2 minus 2 bracket 3. The same thing is going to happen at the end. Don't forget that subtraction is a special type of addition. That is why each time we give a law that involves addition and subtraction, a composite sign called plus or minus is used. Don't forget the case of like terms. That was the case with it, where we had to replace that plus sign with a composite sign of plus or minus. So, if you repeat this experiment with subtraction, you discover that it is also reducible. Therefore, we conclude that it is not possible to get a final simple answer if we are to add two or more unlike terms, or to carry out subtraction with two or more unlike terms. Straight away, let us test multiplication. And here comes a numerical experiment on multiplication of unlike terms. 6 bracket 3 to the power 2 times 2 bracket 3. We are carrying out multiplication of these two numbers. First, let us get the answer by default method. By default, we are expected to know what the value of the number here is. That is 9, and then multiply it by 6. And that will give us first 6 bracket 9. Then times the next number, which is 2 bracket 3. So this times this has become 6 bracket 9 times 2 bracket 3. Still by default, we're supposed to get the value of 6 bracket 9 and multiply it by the value of 2 bracket 3. The value of 6 bracket 9 is 54, and the value of 2 bracket 3 is 6. And multiplication sign is what comes between them. And that gives us 54 times 6. The result is equal to 324. So the answer to this number operation is 324. This is pure arithmetic. That is because there is no unknown in the entire number expressions. Now let us use or try to use an alternative method to get the same 324. This method is a default method. If we discover any other method that we can apply, which is not this default method that is going to give us this 324, then perhaps that one will turn out to be the source of the law for multiplication of unlike terms. Let us try. 6 bracket 3 to the power 2 times 2 bracket 3 is the same thing as saying 6 times 3 times 3, because 3 to the power 2 means 3 times 3, then times this 6 outside. It means that 6 times 3 represents this. Then times is still there. 2 bracket 3 means 2 times 3. I hope you are following what is going on here. Alright, let us rearrange them commutatively. It means that in multiplication, anyone can come first, because at the end the answer is the same thing. For the purpose, let 6 and 2 be isolated to one side, see them here, and then let all the 3's be quartered to one side, again see them this side. Therefore, this outcome has become this. Okay, let us try to get the result of 6 times 2. It is 12. Then 3 times 3 times 3. Let us put that number operation in index form. That will give us 3 to the power 3. Therefore, this number operation, when compressed further, is equal to 12 bracket 3 to the power 3. 3 to the power 3 is 27. Then 27 times 12 is equal to 324. The same 324 we got earlier using the default method. Now think about it. If everywhere 3 appears, we replace the 3 with y. How far can the number operation go in terms of producing the answer? recall that this is an answer to this number operation. This is also an answer to this number operation. This is an answer to the same number operation, as well as this 3, 2, 4. It means that there are 4 different answers to this number operation. If I replace this 3 and this 3 by y, can I still go as far as saying that the answer is 3, 2, 4? No. But can I go as far as saying that the answer is equal to 12 brackets that y to the power 3, since 3 will be replaced by the y? Please, it is not this 3 that y will replace. The power is not what y replaced. It is the number in the bracket. The base of the index in the bracket is what this y is going to replace. So it is not this 3. It is just a coincidence that this 3 looks like this one. But it is this base that y is replacing. If y replaces this 3, can the answer go as far as here? Yes, it can. Let us see. Now see it. It says this is 6y to the power 2 times 2y. When expanded, we give us this 6 times y, because y to the power 2 is y times y. And times this 6, see it here, and times, see it here, and 2, 32, and times y again, see it. We've simplified. We have that this turns to 6 times 2 times y times y times y. I hope you know why this can become this. Alright, then in the end, we have that 6 times this 2 is equal to this 12, but y times y is equal to y to the power 3. So this last answer is how far we can go. We can't go beyond it to get this 3, 2, 4. The reason is that y can represent anything. That y represents 3 in this case does not mean that any other place you see y, that it represents 3. For the fact that the value of y can change anytime, it is improper to write the answer as 3, 2, 4. So the last stage we can take as our answer to this number operation is this, corresponding to this place, 12y to the power 3. We therefore conclude that it is possible to get a simpler answer when we multiply unlike terms. Just to watch it, 6y to the power 2 and 2y are unlike terms. And after we multiply them, they simplified out. The answer is 12y to the power 3. Let me now try to write a kind of a mathematical law, a theory, for that matter, that is used for multiplying unlike terms. Before I do that, let me point it out that 6y to the power 2 and 2y are unlike terms because of one thing. The variables are the same, but they differ in power. So the next law I'm going to write in this space will not represent the multiplication of all kinds of unlike terms. Instead, the law will represent the multiplication of 2 unlike terms that possess the same variable, but the variable exists in different powers. Please permit me to use this space to write the law of multiplication of 2 unlike terms that differ in power only. And here comes that law. AB to the power x times CB to the power y is equal to AC, then in bracket b raised to the power x plus y. You might wonder, what happened here? Does it conform to this law? The answer is yes. Notice carefully that there is a close link between this number operation and this result. First, 6 times 2 is what gave us this 12. Because y is here and y is here, one y was chosen. The power of y here is 2 and the power of y here is 1. So we got this 3 by saying 2 plus 1. The same thing applicable here, x plus y. That means our x is 2, our y is this 1 here. So at last, x plus y is equal to 2 plus 1, and that gave us this 3. So eventually, we accepted that when 2 unlike terms multiply and they have the same variable but in different powers, and then they have different constants that quantify them, that this is the way to simplify it. All right, let us look at the division of unlike terms and then find out whether it is possible that they simplify out. Please follow through. And here comes a numerical experiment on the division of unlike terms. 6 bracket 3 to the power 2 divided by 2 bracket 3 by default is going to give us something like this. This is 6 bracket 9 divided by 2 bracket 3. 6 bracket 9 is 54. 2 bracket 3 is 6. When 6 divides 54, the result is equal to 9. Then let us try a different method we can apply to get the same 9 as the result. If there is no other method available to us, which we know that we can use to carry out the same number operation to get the same 9 as the answer, it means that we don't have a law or alternative method of doing it. But here, we do have a different way of doing it, and that is what happens here. 6 bracket 3 to the power 2 divided by 2 bracket 3. It's the same thing as saying 6 times 3 times 3 over 2 times 3 times 1. I hope you know where we got this 6 times 3 times 3. It is from here. See, the 6 is here, then bracket means that times is between them. See it here. 3 to the power 2 means the same thing as 3 times 3. Right, divide by, this is 2, see it here, times 3, see the 3 here, times 1. This 1 is just introduced to equalize the number of participating numbers that are found on top and those ones below. The dividend has 2 numbers participating, and the divisor must have the same number. That is for a reason you will see later. Now, by applying the law of association, we have this is 6 over 2, see it here, times 3 over 3, see it here, times 3 over 1, see it here. Once we simplify all of them if possible, when to divide this 6, we still have 3. When to divide this 3, have 1, it goes away, times 1 here. Then when 1 divides this 3, it is this 3, and all to the power 1. Therefore, the answer is 3 times 3 to the power 1, or 3 bracket 3 to the power 1. If you say 3 times 3 to the power 1, the answer is equal to 9. The same 9 we got using default method. And now we have used alternative method, the same answer, 9 is gotten. Now let us replace every 3 by y and see what the result turns out to be if we carry out this division of unlike terms. See it here play out. It is 6y to the power 2 divided by this 2y. It is 2y to the power 1. I hope you know that. When done differently, it is 6 times y over 2 times y. When simplified, what we get is 3y to the power 1, otherwise 3y. This conforms to this, except that this 3 is still where it is, and this 3 is replaced with this y to the power 1. At this point, we cannot take it up to 9 as the answer. The reason is that we don't know what this y is. That y used to the 3 does not mean that any place you see y, that it is equal to 3. Therefore, we can go as far as this point, but not this last point. What will you say is the law of dividing unlike terms, in which the two unlike terms possess the same variable, but the variable has different powers in both places where it occurs? Let me use this space here to write the result of division of unlike terms, where the difference lies only in the power. And here comes that result. A b to the power x divided by c b to the power y is equal to a over c, all in brackets, then b raised to the power x minus y. Let us compare it with the result we got from here. 6y to the power 2 divided by this 2y is equal to 3y to the power 1. In this case, our a is this 6, our c is this 2. So if we carry out A over C, it means 6 divided by 2, and that will give us this 3. The next is that this our B, in this case is Y. Y is the place. How did this power 1 come to be? It may have come, in fact it has come right by saying 2 minus 1. The power of Y here is 1 and power of 2. The power of Y here is 2. So 2 minus 1 is equal to 1. If this had been power of 3, it should have been 3 minus 1 to give us power 2. If the power here had been 5, it should have been 5 minus 1 to give us power 4. But because we have power 2 and we have power 1 here, the result is 2 minus 1, and that is equal to 1. I believe that this law is actually what stands for what has transpired for this second line of action, which is alternative method of dividing unlike terms. So far, we have seen how to multiply and divide unlike terms, in which the only difference is that the powers of the countees are different. The same 3 is here and here, but the power of 3 here is 2, and the power of 3 here is 1. What about unlike terms, in which the main difference is that the countees are entirely different? The powers might be the same thing, but the countees are just not the same. Let us look at such unlike terms that differ in every way.